also have a random process where you have an integer valued variable which can either increase or decrease. So the staircase goes up or down, and that is the famous random walk problem. So let me write that down, since we will come back to it over and over again. So let us look at random walk, a simple random walk on a linear lattice. We could do this problem in discrete space and discrete time, or discrete space and continuous time, and continuous space, continuous time, etc. We will do it here for discrete space and continuous time, and then we will go on to the continuous space when we talk about the diffusion equation. So what I have in mind is an infinite linear lattice extending both ways, and you have a random walker on this lattice. And what the walker does is to toss a coin, and if its heads moves to the right, if its tails moves to the left, one step at the end of every time step. This would be a simple random walk. But now we put a little wrinkle on it and say that the coin tossing is done at random instants of time. So the walker may stay at some particular site for an arbitrary amount of time and then take a jump with a mean jump rate lambda once again. And let us label these guys without loss of generality. Since it is an infinite lattice, I will call this site 0, this is site 1, site 2, this is some general site j, and similarly -1, -2 on this side. Okay. And we now seek the probability that if the walker starts from site j equal to 0 without loss of generality, we will start like the starting site to be 0. What is the probability that the walker is at site j at time t? Subject to the initial condition p of j0 equal to delta of j comma 0. This choice of the initial site to be the origin is only possible if you have an infinite lattice on both sides, then there is translation invariance. Otherwise, if you have boundaries, then of course it matters where you start, and then there are very interesting effects, but we will start with this simplest case of a random walk on an infinite linear lattice with this proviso that the mean time of mean rate of jumps out of this site is lambda, some lambda. So in a given interval of time delta t, the probability that a jump occurs to the right or left is lambda delta t, and that no jump occurs is 1 minus lambda delta t. We will make life a little more interesting and say that the probability of a jump to the right is some little p, and the probability of a jump to the left is some little q, where p plus q equal to 1. So there is a little bias in the coin, and the random walker will move to the right with probability p and to the left with probability q at each jump. Okay. Then what is this equation going to be for dpj p of jt over dt equal to? Well, exactly as in the previous case, it is clear that if in time delta t you must go to the site j, if this is site j, then at time t minus delta t you should either have been here or you should have been there. We are not talking about the first passage time probability, that is a much more intricate question. So it is also solvable, and we will do that sometime, but we are not asking about what is the first time you are going to hit this j. At time t you could have gone very far away, you could have come back, so we do not care, all possibilities are included. We would like to have the probability that you are exactly at j at time t. So at time t minus delta t you should have arrived at time either site j plus 1 or site j minus 1. If you arrived at site j minus 1, then you jump with a probability lambda p, p of j minus 1 t. That is the mean rate of jump, and that is the a priori probability that the jump is to the right, and that is the probability that you hit the point j minus 1 and have taken a jump to the right in time delta t. I have moved that delta t to the left, divided, and so on and so forth. Similarly, there is a lambda q p of j plus 1 t, that is the probability that you are at j plus 1 and have jumped back with a probability lambda q. But you could also have been at the site j already at time t and t minus delta t, and in that interval delta t jumped out. So that probability is minus lambda p of j t, lambda times p plus q, but that is unity. So that is the differential equation now, where we have allowed for a bias in the walk. And the question is, what is the solution for this given this thing here, this initial condition here. Once again we use Laplace transforms, we solve this equation as before. What is going to happen? And now we are not worried about P0 playing a special role or anything like that, because there is an infinite lattice, j can increase as well as decrease. So this equation is applicable to all j. Okay. What should I do for the generating function? I define an f of z comma t equal to a summation p of j t z to the power j, and I pick out the coefficient of z to the power j, but j can take plus and minus values, positive and negative integer values. So this summation runs from minus infinity to infinity. What sort of series is this? It is not a power series. It is a Laurent series. It is a Laurent series now, because there are negative powers of z as well, but it is okay, we know how to invert those series as well. We use contour integration to do that. So we need to write this down, write the equation down in this case for the generating function, and then ask what happens to this guy. So let us see, it says delta f over delta t equal to, well, this term here is just going to give me a lambda times f on this side. So there is a minus lambda f on that side, and then what are these terms going to give you? Well, this is z to the power j is multiplying it, but there is a j minus 1 here. So we should convert that to a j minus 1 and then shift j to j minus 1, the summation, and you get f once again. So it is immediately clear that you are going to get lambda times p times z, because you have a z to the power j and you want to make it a j minus 1, so you pull out a z, and here you got a z to the j, but you need a z to the j plus 1, therefore you divide by z, right. So pz plus q over z minus 1 times f, and that is it. Now that is an easy equation to solve, it is just an exponential. So it says f of z comma t equal to e to the power minus lambda t e to the power lambda t times pz plus q over z in this fashion, multiplied by f of z comma 0. But what is f of z comma 0? What is the initial condition? It is not 0 this time, because f of z comma 0 is p of j comma 0, but that is a delta function, Kronecker delta at j equal to 0, equal to 1, because you set j equal to 0, z to the j becomes 1. So I do not need this is 1. So I have an explicit solution, and I need the z to the j power in this, plus or minus, we do not care from this thing here, but that is a Laurent series now, it is not a power series. So you need to use the formula for the Laurent series, do the integral and so on. But actually this is a known function. It turns out that this quantity summation j equal to minus infinity to infinity z to the power j and then a Bessel function ij of So let me write this out. The generating function for t over 2 z plus 1 over z, this is equal to summation j equal to minus infinity to infinity ij of t z to the power j. This thing here, this exponential form, is the generating function not of the Bessel functions of the first kind, but the modified Bessel function of the first kind, defined in this fashion. So let me define this quantity. I nu of z is exactly like j nu, it is n equal to 0 to infinity z over 2 to the power nu plus 2n over n factorial gamma of nu plus n plus 1. It is exactly the same as the Bessel function j nu, except that this factor minus 1 to the power n is missing in the summand. This is also an entire function. In fact, as you can expect, there is a close relation between I and j. If in the original definition of j you had made z equal to iz, there was a z squared to the power z to the power 2n, so there had been a factor I squared to the power n, which is minus 1 to the n. So it is immediately clear that j nu of z and I nu of z are connected by an equation of the form j nu of iz, I times z, is proportional to I nu of z. It is also an entire function, satisfies this modified Bessel equation and so on. But we have that at hand and we know all the properties of this I nu. So can we use that here? Can we read it off? Can we read off the coefficient of z to the power j? Not quite, right? Because you got a z plus 1 over z, but you got a pz and a q over z. If p equal to q equal to half, then you have no problem, because that half comes out and you have precisely this half here, and then of course you can read off z plus 1 over z. But now you got this unsymmetrical thing. The probability of a jump to the right and to the left are different from each other. We would like to make that a symmetric thing. What should you do? Well, yeah, a very simple trick, of course, is to immediately say this thing here is equal to e to the minus lambda t. It is a cheap trick. Lambda t, square root of pq, take out square root of pq, and then you have inside z times square root of p over q plus 1 over z times square root of p over q. Isn't it? So you just take out square root of pq and then of course it becomes symmetrical. So this immediately implies right away that pj, p of j comma t equal to e to the minus lambda t, that is going to sit here all the time, multiplied by, we want the coefficient of z to the power j. So there is this factor always appearing along with z to the power j. So you have p over q to the power j over 2 multiplied by ij. Oh, there was a 2 here in the generating function, so you got to put that 2 back, and that is the solution. So the explicit solution to this probability is some exponential factor e to the minus lambda t multiplied by this bias factor, which disappears when p equal to q, and then this modified Bessel function here, which is an entire function of its argument, and we know it, we can define it via its power series. So we have an explicit solution to the random walk problem, biased random walk problem in one dimension. What we need to do is to extract interesting information from it. For instance, if you do not have a bias, then it is clear that the probability of being at plus j must be equal to the probability of being minus j at any instant of time by symmetry in this problem. So no bias, p equal to q equal to half. This implies that p of j comma t equal to e to the minus lambda t ij of lambda t. Oh, by the way, I forgot to mention that ij of anything, say, is equal to I minus j of z. I already mentioned that for the Bessel function j, when nu was equal to an integer, then j minus n and jn are not linearly independent of each other. Translated, for the modified Bessel function, they actually happen to be exactly equal to each other. In the Bessel function case, you would have a minus to the n factor, but here it is just exactly the same, these two. So this immediately says that Pj equal to P minus j, as you expect when you do not have any bias at all. The other point is, what happens for long times? Very nice, you started off at the origin and then you did this right, left, etc. What happens for very long times? Okay. Not surprisingly, you can show that the average value of j is actually 0 at all times, and that is not surprising, because how do you define the average value of j? This function is normalized to unity, because we started with a differential equation in which we looked at all the possibilities. Probability is conserved completely. So at any time t, the walker has to be on some site j from between minus infinity and infinity. So the total probability is unity. You sum this over j from minus infinity to infinity, you are guaranteed to get 1. Okay. Now the question is, what is this equal to? Since this is normalized, it is clear that this is equal to j times p of j comma t summed over all j, and what is the value of that? What would you, yes, definitely, because you expect that the walker might have taken at any instant of time, the mean displacement of the walker from the origin is going to be 0, okay? Because there is as much probability of the walker moving to the left as there is of her moving to the right. Okay. So this is identically 0, because this is an even function of j and that is an odd function, so the sum is obviously 0. Okay. What is not 0 is the mean square displacement, that is not going to be 0, and that is going to be very interesting for us. J squared of t equal to summation j squared p of j comma t, and what do you think that is going to be? Well, you can see that we are heading towards the problem of diffusion, right. So it is clear that there is a random walk going on, and when the step size is going to become 0, then it is going to go over into unbiased diffusion of some kind. Now diffusion, of course, you know that the root mean square displacement is famously proportional to the square root of the time. So the mean square displacement, since the mean displacement is 0, this is the mean square displacement, it's equal to, this turns out to be exactly equal to lambda t. I would like you to prove that. There is enough material here to be able to do that very easily. In fact, you should be able to do this using the generating function. What would you do? Go back to the generating function. Suppose you do not know the properties of the Bessel functions. Remember that f of z comma t was equal to summation j equal to minus infinity to infinity p of j comma t and then z to the power j. Derivatives with respect to? With respect to z. So it is clear that delta f over delta z at z equal to 1, differentiate and then set z equal to 1, f of z 1 comma t is equal to 1, because that is normalization. And if you differentiate this, you pull a j here and then set j equal to 1, so this is exactly equal to j of t. So to establish this result, which we saw in the unbiased case in a trivial way, all you have to do is to take this quantity, differentiate it once, we know the explicit expression for it there even in the biased case, differentiate it and you end up with the mean displacement. What would you expect is the mean displacement in this instance? In the biased case, what would you expect? Would it be 0?
No, something.
Well, if P is greater than Q, it is clear there is a bias to the right. So you would expect a positive value of J of t. If P were less than Q, then you would expect a negative value, right. So you would expect, very crudely speaking, that the mean value J of t is proportional to P minus Q, which is acting like some kind of drift. All you have to do is to differentiate once and verify that for yourselves. You need the value, so once you put this in here, you can compute explicitly what the various means are in any case from that exponential expression. That is the easiest place to do it. This thing here turns out to be lambda t once again in the case when you do not have a bias. When you have a bias, what would you expect is this value? What would you expect? Now you see what is going to happen is that this walker, if she is completely unbiased, the random walker, then she moves to the right and left with equal probabilities, vacillates, and on the average does not get anywhere, displacement, but the mean square displacement goes like lambda t, which means the root mean square displacement goes like the square root of time. In this problem, for all time this happens, but in general when you have a diffusion process, only in the limit of what is called the diffusion limit would this happen, but this random walk is essentially free diffusion. In the presence of a bias, you would expect a systematic drift to one side, which means that you essentially have a velocity, a drift velocity to one side. Then the mean square displacement will become proportional to the square of the time, because there is a velocity, a drift velocity available. But when P equal to Q, that is not present and you have this pure diffusive behavior. I want you to keep this in mind, that in unbiased diffusion the mean square displacement is proportional to the first power of the time, because when we solve the diffusion equation next in continuous space and time, this is going to become a very crucial feature. Can we generalize this to higher dimensions? Suppose you have a lattice in higher dimensions, square lattice or a cubic lattice or some hypercubic lattice in any number of dimensions. Can we generalize this? Well, now you have to tell me what are the probabilities of moving in various directions. So suppose you are in 3 dimensions or 2 say, then there is an up down and a left right, and each site on a square lattice has 4 nearest neighbors. So we could say, okay, with probability 1/4 the person moves up or down or right or left. In 3 dimensions there is a back and front as well, so 1/6 and so on. So it is immediately clear that if you did this in any number of dimensions, you write an equation like dp over dt for the vector j at time t. The vector j is specified by a set of lattice points. Each j, component of j, is an integer from -infinity to infinity, and let us say you are working in d dimensions, so j equal to j1, j2, jd. Each of them is an integer. ji is an element of a set of integers. This is equal to, now what is the master equation you are going to write down? How do you write this down? First there is a gain term, you should have reached a nearest neighbor site of this site j, and then you jump into this site j. How many nearest neighbors are there in d dimensions? In 1 dimension there are 2, in 2 dimensions there are 4, in 3 dimensions there are 6, so there are 2d in d dimensions. So this should be obviously lambda over 2d, because it is completely unbiased in this case, times p of j plus a nearest neighbor delta, some nearest neighbor vector at time t summed over these nearest neighbors delta. So up, down, front, back, left, right, etc. sum it down, minus lambda times p of j comma t. So this guy here is the nearest neighbor vector. That is the master equation. and you could do exactly the same trick as before. In fact, we could go one better. We could even say, look, I am going to have a bias. So in a particular direction I will have a bias Pi and Qi in the component I. So it is P1 and Q1 for left right, P2 and Q2 for front back, P3 and Q3 for up down, and so on. I write exactly the same equation down, and it is immediately obvious that this guy factors completely. Each time I pull out a square root of Pi and the whole thing factors. So we can in fact write the exact solution down. It is equal to Ij, not a single j, but it is going to be Ij1 P1 Q1 I order j2 2 lambda t square root of P2 Q2 dot 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 all the way to the end, and this is going to be a product I equal to 1 to d Pi over Qi Ji over 2 in this fashion. So we could just write this as Ji, Pi, Qi, and forget about these. That is going to be my P of J. That is the exact solution to the random walk problem in hypercubic lattice of d dimensions with bias factors Pi and Qi for each direction. The question is what happens at very long times. Remember, this probability has to be normalized. So it is clear that this factor here cannot increase too rapidly, not faster than this anyway, must provide a damping factor here. And in fact there is a very simple asymptotic formula which says I nu of z goes as mod z tends to infinity like e to the power z over square root of 2 pi z, independent of nu. So in the unbiased case, this factor e to the lambda t minus lambda t is cancelled exactly by I nu of lambda t, and you have a pure power law decay. But when you have a bias, there is also an exponential decay because the whole probability mass is shifting. We will come back to this, we will look at this in some more detail and understand where this random walk problem goes over into the solution of the diffusion equation. In particular, we will see how this very strange looking thing, this modified Bessel function, when you make the lattice constant go to 0 and you go to continuum, a spatial continuum, it will go over into a Gaussian function, and that will be the solution to the diffusion equation. Provides an interesting connection between this and the Gaussian. It is called the central limit theorem, and we will do this in some detail a little later. So here is a place where we use Laplace transforms in a simple way, but let us think just for a second about the physics behind this. We got first order differential equations in time, and they were fairly easy to solve. You do not need Laplace transforms for that at all. Why did we get first order equations in time? What was the physical assumption that led to this first order equation? I already mentioned that these are examples of what are called Markov processes. The point is, we wrote an equation for first order because what happens to P of n, for instance, or j at time t plus delta t depends on what happened at time t, at the immediate previous instance, not on things before that. In other words, the future is determined by the present state. So all conditional probabilities depend on just one time step before, and that is the Markov assumption. Had we had any history dependence saying how you got to that state, then of course you would have higher order differential equations, and then the matter would become a little more complicated. So if there had been some memory in this problem, if the random walker, as she is taking this random walk, says okay, it is true that at each site I flip a coin, I move to the right or left with some probability, but if those probabilities also depended on a memory of in which direction had the previous step been taken, had it been from the left to this point or had it been from the right to that point, it is like remembering not just the position but also the momentum. And then of course you have second order and higher order differential equations. That is called persistent diffusion, and it has its own interesting and mathematical solutions. So it is a one step process. it remembers both position and velocity. And I mention this because when we talk about the diffusion equation, we will see that what is happening there is that you are only talking about the position of the diffusion particle, not its momentum. But if you wanted to do the same thing in phase space, then you have to worry about the position and the momentum, and then the equations get higher order differential equations in time. So it is always worth remembering that. For first order equations, the Laplace transform method is practically not necessary, but for higher order equations it gets more and more useful. Okay.